this function is equivalent to 1 over s, which is the equivalent complex frequency domain. So, in order to come up with 1 over s, let ut is equals to 1. So, we have come up with this expression, which is the integration of 0 to infinity e raised to negative st dt. So, performing the integration, we'll come up with negative 1 over s e raised to negative st. So,
Go.
So we will be substituting we'll be getting the limits. So negative 1 over s times the limits of negative st, which is e raised to negative times the infinity minus e raised to negative s times 0. So any number raised by any number raised to infinity is equals to 0. So this will be 0. And any number raised to 0 will become 1. So we have subtraction here, so this will be positive. So negative 1 over s times negative 1 is 1 over s. So we will be proving that this function is equivalent to 1 over s squared, which is its equivalent complex frequency domain. So Laplace of tut equals to integration of 0 to infinity e raised to negative s to t ut dt. So we will be setting ut to 1. So we will come up with this expression. To simplify this expression, we will be using integration by parts. So our u will be t, and its derivative is dt. So our dv will be e raised to negative st dt, and its integration is negative 1 over s e raised to st. So substituting all the values to the formula, we'll come up with negative 1 over s e raised to negative st t minus our dt, which is negative 1 over s rather, e raised to negative st dt. So we factored out the constant, which is negative 1 over s. So this will be the result. So performing basic integration, so the result will be bring this expression down. Negative 1 over s e raised to negative st t plus, because we have subtraction here and our constant is negative, so this will be plus 1 over s, and the integration of this is negative 1 over s e negative st. So combining simplifying this expression, this will be the result. So now we will factor out the constant, which is negative 1 over s. So the result will be this. Then we will be performing the limits. So substituting this, this will be the result. Negative 1 over s times e negative s times the infinity, then times the infinity, plus 1 over s e raised to s times the infinity, then minus e raised to negative s times 0, plus 1 over s e raised to negative s times 0. So any number raised to infinity and multiplied by raised by infinity rather, and multiplied by infinity will be 0. This will be 0 too. And any number multiplied by s, multiplied by 0 rather, times 0 this will be 0. And this will be 1 because any number raised to 0 is 1. So simplifying this, we have come up with negative 1 over s times negative 1 over s. So the result will be 1 over s squared. So today we will be proving that this function is equivalent to 1 over s minus a, which is the equivalent complex frequency domain. So Laplace of e raised to 8e ut is equivalent to integration of 0 to infinity of e raised to negative st times e raised to 8e ut dt. So we have the rule in law of exponents that if the bases are the same, we can combine the exponents. So we have come up with this expression. So applying the basic rule of integration, which is integration of e u du is equivalent to a times e raised to au, we have come up with this answer. So as we can see in this expression, before we integrate in this expression, we factored out the negative. So because we have a rule in the limits that if the upper limit is infinite, the exponent must be negative. So evaluating this expression, negative 1 over s minus a times e raised to negative s minus a times infinity minus e raised to negative s minus a times 0. So any number raised to infinity is equivalent to 0. So this will be 0. And any number raised to 0 will be 1. So this will be 1. So we have an operation here which is subtraction. So we have come up with negative 1. So negative 1 times negative 1 minus 1 over s minus a is 1 over s minus a.
So we will be proving that this function is equivalent to n factorial over s raised to n plus 1, which is the equivalent complex frequency domain. So this term is equals to integration of 0 to infinity e raised to negative st and dt. To simplify this equation, we will be using integration by parts. So our u will be tn, du will be nt raised to n minus 1 dt, and dv will be e raised to negative st dt, and its integration is negative 1 over s e raised to negative st. So we will be plugging in these values into the formula, which is uv minus integration of v du. So after doing the basic integration, we have come up with this expression. So as you can see, we already put the limits, and we will be evaluating first the uv side. So limit of infinity minus limit of 0 is 0 minus 0. So at this side, which is the minus and integration of v du, we will be moving all the constants out, which is negative 1 over s and n. So we have come up with plus n over s, integration of 0 to infinity of e of this term rather. So therefore, Laplace of Tn is equals to n over s times the Laplace of t raised to n minus 1. So how did we get this? So as you can see, this term is terminating or continuous. That's why we have come up with this expression. Now to prove that this expression is terminating, we will be plugging in the values of n, which is 1, 2, and 3. So at n is equals to 1, Laplace of t raised to 1 is equals to 1 over s times the Laplace of 1. How did we get the Laplace of 1? So we will be, as I said a while ago, we will be plugging in the values of n. So first at n is equals to 1. So from the formula, which is this, Laplace of t raised to 1 minus 1 will become Laplace of t raised to 0, which is meaning any variable or number raised to 0 will become 1. So this became Laplace of 1. And Laplace of 1, as we all know, is equals to 1 over s. That's why we have 1 over s here. So performing the operations, so 1 over s times 1 over s is 1 over s squared. So at n is equals to 2, at n is equals to 2, the same procedures we have done like the first one. Laplace of t raised to 2 is equals to 2 over s Laplace times the Laplace of t raised to 1. So the Laplace of t raised to 1 is equals to 1 over s squared. That's why we have 1 over s squared here. Then perform the operations. We have come up with 2 factorial over s cubed. So at the same procedures in n is equals to 3. So Laplace of t raised to 3 is equals to 3 over s times the Laplace of t is t raised to 2. So the Laplace of t raised to 2 is 2 factorial over s cubed. That's why we substitute here. So we have come up with 3 factorial over s raised to 4. So therefore, the Laplace of before that, as you can see, as we increase the values of n, the denominator is increased. The exponent in the denominator is increasing, so as the numerator. So therefore, we conclude that Laplace of t raised to n ut dt is equals to n factorial over s raised to n plus 1. We will be proving that this function is equivalent to n factorial over quantity s minus a raised to n plus 1. So this term is equal to integration of 0 to infinity of e raised to negative st times e raised to at and t raised to n rather dt. So as we can see, in law of exponents, if the bases have or if the bases are the same rather, we can combine its exponents. So we have come up with this expression. So to simplify that, we will be using integration by parts. And we will be plugging in this values into the formula. So we have come up with this expression. So first, we will be evaluating the UV part, which is this. So limit of infinity minus limit of 0 is 0. So we will be proceeding to the minus integration of VD part. So first, we will be moving all the constants out of this expression, which results to plus n over s minus a times the integration of e raised to raised to the quantity a minus s times t raised to n minus 1 dt. So this expression is non-terminating rather, or continuous. So therefore, the Laplace of t raised to n times e raised to at is equal to n over s minus a times the Laplace of t raised to n minus 1 and eat. So to prove that this expression is terminating, we will be using values. We will be setting values for n. So for at n is equal to 1, Laplace of t raised to n and times et is equal to 1 over s minus a times the Laplace of t raised to 0. So this happened because we substituted the value of n in the exponent part. So we all know that t raised to 0 is equivalent to 1. So this will be 1. So we have come up with the plus of e raised to 80. So the plus of e raised to 80 is equivalent to 1 over s minus a. So bring down this term times the plus of E80, which is this, and this will be the result. Same procedure in at n is equal to 2. So Laplace of t2 et is equal to 2 over s minus a times the Laplace of t raised to n and e raised to t, 80 rather. So bring down this term, and the Laplace of t raised to 1 times e raised to 80 is this. So we will be substituting this to this. So perform the operation. So we have come up with this term. So as we can see, as we increase the value of the n, the power in this part is increasing also, so as the numerator. So we will therefore the Laplace of t raised to n e raised to 80 is n factorial over s minus a raised to n plus 1. So we will be proving that cosine bt dt is equivalent to s over s squared plus b squared, which is its complex frequency domain. So Laplace of cosine bt dt is equal to integration of 0 raised to rather to infinity of e raised to negative st cosine bt dt. So, to get the integration of this, we will be using integration by parts, which so cosine bt will be RU, and its derivative is negative b sine bt dt, and dv is e raised to negative st dt, and its integration is negative 1 over s e raised to negative st. So we will be plugging in this values rather into the formula. So after we plug in all of this, so we have come up with this expression. So as you can see, we already put the limits in their respective places. So first, we will be evaluating the UV part, which is this. So the limit of infinity minus the 0 is equal to 0 minus 1 minus negative 1 over s. So at this part, which is the minus integration of VDU, we will be moving all the constants out of the expression. So we have come up with this expression, which is minus b over s integration of 0 to infinity of e raised to negative st sine bt dt. So again, we will be performing another integration. So we will be using integration by parts again using this formula. So sine bt will be RU, and b cosine bt will be the du. dv will be e raised to negative st dt, and v is equal to negative 1 over s rather, e raised to negative st. So we will be plugging in this formula into the plugging in this values into the formula. So we have come up with this expression. So after that, we will be, as you can see, we will be distributing this negative b over s into these terms. So we will be, again, we will be setting y, to Laplace of cosine bt, so that we will be seeing the equation very clearly. So after that, we have come up with this equation, which is y is equals to 1 over s plus b sine bt e raised to negative st over s squared minus b squared minus s over s squared rather y. Then after that, we will be transposing this term to the other side, so that we will get this. We will get the limits of this. So after evaluating the limits, and after evaluating the limits, we will be performing adding fractions, so that we will it will be leading to this, which is s squared plus b squared over s squared y equals to 1 over s rather. So we will be equating this equation into y, so that we will be having the answer. So after that, we will be performing this. So y is equal to 1 over s times s squared over s squared plus b squared. So this will be cancelled, so that y will be equal to s over s squared plus b squared. But we have a condition that y is equal to Laplace of cosine bt. So therefore, Laplace of cosine bt is equal to s over s squared plus bt. So we will be proving that this function is equals to b over b squared plus s squared, which is the equivalent frequency domain. So Laplace of sine bt ut is equals to integration of 0 to infinity of e raised to negative st sine bt dt. So to simplify this equation, we will be using integration by parts. So sine bt will be ru, and its derivative is b cos bt. dv will be our e raised to negative st dt, and its integration is negative s e raised to negative st. So we substitute all the values into the formula, which is uv minus integration of v du. So we have come up with this equation. So as you can see, we already put the limits. So we will be evaluating this. So after evaluating the limits, we have come up with this expression, which is 0 minus 0 plus bs integration of 0 to infinity times e raised to negative st cosine bt dt. So again, we will be using integration by parts to simplify the equation. So our u will be cosine bt, and its derivative is negative b sine bt dt. So our dv will be e raised to negative st dt, and its integration is v is equals to negative 1 over s e raised to negative st. So we plug in the values into the formula of integration by parts. So we have come up with this equation. So we will be distributing negative bs, which is from the which is from the result from the first integration. So we have come up with this equation. As you can see, we have after we evaluate the limits, rather, we have come up to y is equals to b over s squared minus b squared minus over s squared, rather, times y, because we set sine bt dt into y, so we have y on the both sides. So after this, we will be performing adding fractions so that we could simplify the equation. So we have come up with s squared plus b squared over s squared times y is equals to b squared, b over s squared. So we will be combining it, or we will be combining the like terms, so that we will come up with b over b squared plus s squared. So we will be proving that this function is equivalent to s plus a over quantity s plus a squared plus b squared, which is equivalent complex frequency domain. So Laplace of e raised to negative 80 cosine bt is equal to integration of 0 to infinity of e raised to negative st times e raised to negative 80 cosine bt dt. So we have a rule in exponents, law of exponents, rather, that if the bases are the same, we could combine its exponents. So we have come up with this equation. So we will be moving the negative out of the out of this term, so we will be having this equation, which is integration of 0 to infinity uh, of e raised to negative s plus a, a quantity s plus a rather, times t cosine dt. So we will be, in order to get the answer for this, we will be using integration by parts. So our u will be cosine bt, and its derivative is negative b sine bt dt. Our dv is e raised to negative quantity s plus a times t dt, and its integration is negative 1 over s plus a times e raised to negative quantity s plus a times t. So we will be plugging in all we will be plugging all of this into the onto the formula, which is uv minus integration of v du. So after that, we will be having this equation. As you can see, we already placed the limits on their respective places. So first, we will be getting the limits of the uv. So the limits of limit of infinity minus limit of 0 rather, will be equal to 0 minus quantity negative a over s plus a. Then after that, we will as you can see, we will also we will going to use integration by parts again for this term. So our uv will be sine bt, and its derivative is b cos bt dt. dv will be e raised to negative quantity s plus a times t dt, and its integration is negative 1 over s plus a times e raised to negative s plus a times t. So after plugging all of this into the formula of integration by parts, we will be having this expression. So after that, we will set y. We will set this term into y, so that we will be seeing the equation clearly for us to solve it easily. So after that, we will be distributing the negative b over s plus a. So after that, we will be, and after that, and after we evaluate the limits, we will be having this equation, which is y is equals to 1 over s plus a minus b over s plus a times quantity 0 plus b over s plus ay. So after that, we will be distributing this to this term. So the result will be this expression. After that, we will be simplifying this equation, so that we will see clearly which is the answer for this. We will be getting the Laplace of this function. So the answer will be quantity s plus a squared plus b squared over s plus a squared times y equals to 1 over s plus a. So we will be equating this equation to y, so that we will be having the answer. But we have a condition that y is equals to integration of 0 to infinity e raised to negative s quantity s plus a cosine bt. So therefore, the Laplace of e raised to negative 80 cosine bt is equal to s plus a over quantity s plus a squared plus b squared. For the last function, we will be proving this to its equivalent complex frequency domain, which is b over s plus a squared plus b squared. So the Laplace of e raised to negative 80 sine bt is equal to integration of 0 to infinity e raised to negative st times e raised to negative 80 sine bt dt. So we have a rule in law of exponents that if the bases are the same, we could combine its exponents. So we have come up with this. After that, we will move the negative out of this term. So we have come up with this expression. So to get the integration of this, we will be using integration by parts. Ru will be sine bt, du will be b cos bt dt, dv will be e raised to negative quantity s plus a dt, and Rv is the integration of this, which is negative 1 over sa e raised to negative quantity plus a. After we plug all of this into the formula, which is uv minus vd minus integration of vdu, we have come up with this. And as you can see, we already put the limits on its respective places. So we will be first evaluate the uv part. So limit of infinity minus limit of 0 is equals to 0 minus 0. And for the minus integration of vdu, we will be move all of the constants out of this expression. So because this is 0, this will be cancelled. So we will bring this whole expression down. And as you can see, we will be getting again the integration. So we will be using integration by parts again. So same procedure as the first one. So we will be getting the u, which is cos bt, its integration, which is negative b sine bt, dv, which is e raised to negative s plus a dt, and its integration is b is equals to 1 over negative 1 rather over s plus a e raised to negative quantity s plus a t. So after plugging all of that into the formula again, we have come up with this expression. So we will be assigning y as the sine bt raised to negative raised to negative s plus a dt. So that we will see the whole expression clearly and solve the function easily. So after that, we have come up with this. Y is equals to b plus s over s plus a rather times quantity 0 minus negative 1 over sa minus b over 1 quantity s plus a times y. So after that, we will perform some adding of fractions, which leads to this expression wherein y is equals to b over s plus a squared minus b squared over quantity s plus a squared y. So after that, we will be using the subtraction of fractions. So which leads to this expression, which is y times quantity sa squared plus b squared over sa squared is equal to b over s plus a squared. So we have a condition which is y is equals to sine bt e raised to negative s plus a dt. So we therefore conclude that Laplace of e raised to negative at sine bt is equals to b over s plus a squared plus b squared.